Hello and welcome again. I'm Bob Falconer. This presentation explains the development of the theory behind the MARFLEX system of masonry arch strengthening. There's been much talk of masonry bridges being strengthened unnecessarily, mainly by academics with limited practical experience. I have to say here and now that we've never installed our system into a masonry arch barrel without good reason. Sometimes we don't strengthen barrels, we just bridge extensive cracking. Sometimes, where there is no evidence of cracking, we only insert radial pins to cure confirmed ring separation and allow the rings of the barrel to act as one unit. As I said previously, I am a director of Goldhog Bridge Restoration Limited, the company that installs the system, though I will be giving a personal perspective rather than a company one. Masonry bridges are an important part of our rich heritage of historic structures. They are the most aesthetically acceptable type of bridge and commonly appear in landscape paintings and photographs. This photo of the Sheepwash Bridge was a holiday snap taken by a friend of mine. As we have seen in the last presentation, masonry bridges can tolerate large deformations and still be capable of carrying load. They have usually been built from local materials and can last indefinitely with minimal maintenance. They are part of our heritage and possibly the most environmentally friendly and useful structures on the planet. They must be preserved using methods with minimal carbon footprint wherever possible. The main cause of failure of masonry bridges tends to come from loss of support from scour, mainly from floodwaters. Most problems come from overloading and serviceability issues, including neglect, as covered in the second presentation of this series. There's much discussion on the most appropriate method of analysis, some sensible and some not so. Our MARS design software, called MARFLEX, is a development of our ASARC program, which was written in the 1980s and based on Professor Pippard's experiments of the 1930s. I do have a high regard for Professor Pippard's work. As experienced masonry bridge assessors, we used Pippard's approach as this gave results that were useful for assessment engineers, giving us the actual design capacity and the recommended weight restriction where appropriate. The approach is based on the progressive development of 4 hinges under increasing load. So as the load increases beyond the design load, hinge 1 at C forms. Then, as the load increases further, hinge 2 comes at D, then hinge 3 at B, and then finally hinge 4 at A, leading to a mechanism and thus failure. Pippard's approach was quite basic, and we modified it to accept load distribution, lateral and vertical pressure distribution from fill and load, a design masonry strength with different profiles and varying barrel thicknesses, checks for spring back and 5-hinge failures, and calculation of differential shear between the rings. The line of thrust is constrained within a core that is determined by the compressive strength of the masonry. Our ASARC program of masonry arch analysis came about from the Operation Bridgeguard exercise. Chertsey Bridge over the Thames appeared on my desk in 1984, and I was given the task of analysing it. There was no software available for this task at the time, and as Pippard's approach was iterative, I wrote a piece of software to speed up the calculations. One of our major clients, Surrey County Council, then asked for a copy of the software, and so the essence of ASARC was born. As an aside, Chertsey Bridge was a lesson in contract administration. The contractor did build the bridge from one side of the Thames to the other as per the contract. The contract didn't specify that the bridge should connect to the roadways at each end, and so the authority was left with a bridge that no one could use. Additional arches had to be constructed at each end to give access. It took about 2 years to add all the bells and whistles to ASARC, and when the commercial version was available, along came Bill Harvey's Archie. Most bridge authorities bought both programs as a check on each other, and the program did very well. ASARC was independently assessed by OVARP in 1999, the conclusion being that it was the most accurate program available at the time. This is the ASARC program. Parameters are entered using drop-down menus. This menu covers the barrel profile, multi-span and road profile. This enters the fill profile. This defines the fill profile. This enters the unit weights. This recommends material strengths. This recommends a condition factor as per CS 454. This states whether or not axle liftoff is a possibility. This gives the user a choice of different approaches to lateral pressure distribution. This gives the lateral pressure parameters, and this is the lateral pressure coefficients. I've added the results for ASARC to this table of load tests on redundant bridges from BD16. The figures for ASARC were evaluated independently, so I take no responsibility. The ASARC loads are calculated for the position of the test load, which, in most cases, doesn't coincide with the actual critical position. Compressive strengths used to obtain the results are obtained from crushing test results carried out in conjunction with the load tests. Condition factors have not been incorporated in the above results, as their application depends largely on engineering judgment and could be used to fiddle the results. It should be noted that during the test on Bargawa, the load was cycled at a high level before collapse was reached, which may have reduced the capacity of the bridge. Torksey was in poor condition before the test, with cracks in the arch up to 75 mm wide. Strathmashy was cracked longitudinally before the test, and failure appears to originate from this crack. However, the low standard deviation shows the accuracy of ASARC. You can see it's 23 compared to all the others. In 1994, SSP carried out research for the Transport Research Laboratory. This compared stresses in multi-span masonry arches to stresses in a single-span arch for various load conditions. Over 90 finite element models were built and tested. The elastic package we had available at the time meant that I had to write a preprocessor to form the mesh, with each element having an aspect ratio of greater than 1:6. Springs were used for boundary conditions. Numerous permutations of span, 6 meters to 18 meters, rise, pier height, 1 meter to 8 meters, and fill depth, 1/4 of a meter to a meter, were analysed to compare the performance of internal and external spans to the equivalent single span to determine the effects of the piers. The analysis was essentially elastic, with overstressed areas being reprofiled. I'm not convinced there was much wrong with this approach, as masonry arches that we've measured in the field do return to their original position after a heavy load has passed over. Under serviceability loading, they're not as non-linear as many people think. I do appreciate, though, that the fill was modelled as an elastic medium, which of course it isn't. This research gave a formula shown for the effects of the piers. This is the formula here. The results align with the advice given in the original Solog study of 1963. That's the original Solog study, which was written for tank and transporter loading and recommended a factor of 0.8 for internal spans and 0.9 for end spans of a multi-span bridge with a height-width ratio of unity or less. Our study showed that even though simplistic, this is not really too far off the mark. The company I worked for at the time was Structural Survey Partnership under the MD Brian Boughton. I was originally invited to join the company by William Day, who was an ex-colleague from our days at Freeman Fox & Partners, where I had gained some fantastic experience. At SSP, we were mainly concerned with bridge inspection, assessment and repair. In bridge assessment, you really need to have an in-depth knowledge of material behaviour, history of construction and structural interaction. William had this knowledge, and I learned such a lot from our in-depth discussions on each of the bridges that we were assessing. I do think that involvement in bridge assessment is such a good grounding for a proper bridge engineer. We assessed a number of post-tensioned and reinforced concrete bridges. This slide shows a post-tensioning duct that was supposed to have been grouted. We came across a number of these that were full of water. And this petrographic slide shows the effects of carbonation. This slide shows an example of corrosion that we had to take into account when assessing the strength of wrought iron bridge. And this is a trial hole over a troughing deck. We did do a number of load tests on troughing decks, which were quite interesting. The company carried out numerous load tests on various types of bridges. We generally used weighbridge testing lorries. These enabled us to know the axle loads exactly. When load testing, static axle loads need to be increased progressively, normally up to 1.25 times the design load. The vehicles are then driven at the allowable speed to assess the impact factor for the bridge. The impact factor obviously depends on the road profile, bridge position, and irregularities in the surfacing. It doesn't make sense that this is a blanket factor. The advice given in CS 454 goes some way towards rectifying this. A load test on the brick masonry viaduct at Ramsgate in Kent used vibrating wire gauges. We found that the rules for load distribution in the code BD21, which was in use at the time, were actually quite sensible. Unfortunately, after this, the parent company, SSP, was put into administration in the recession in the late 90s. The major players, with thin order books, had realised that there was work still to be had in bridge assessment, and they undercut us in order to get us out of the market. We have seen some of the reports that were published then, and, to be honest, they were not worth the paper they were printed on. With the demise of SSP, the commercial availability of ASARC ended. Fortunately, then, the MARFLEX system, devised and patented by Brian Boughton, came on the scene, marketed by Mars Limited. Every cloud has a silver lining. The MARFLEX system was first used on a bridge near Rochdale. Again, the originators realised that they didn't have a design method for the amount of reinforcement to be used, and this was where I was called in. I used an elastic method initially, which was not ideal, and designed the reinforcement based on this elastic analysis. The bridge in question was load tested after the installation of the system and was found to be able to carry the required load. The load test cost as much as the installation. This meant that the system just wasn't commercially viable. I then had an epiphany. I realised that if a moment of resistance is applied at the critical hinge, and therefore requires a greater load to create this hinge, then all other hinges will be delayed and be able to take this load. So the idea for an analysis method was born. I adapted the ASARC program to insert a moment of resistance at the critical hinge to bring the barrel up to the required capacity for all loading requirements. And the MARFLEX program for designing the MARFLEX system was born. The location of this critical hinge varies for different load conditions and for different vehicle directions. This is why the MARFLEX system uses circumferential reinforcement all round the barrel. This allows for the reinforcement at all critical locations and for adequate anchorage of the bar. Radial pins are inserted to enable all brickwork rings to act together. We don't actually need radial pins in stone barrels of single stone thickness. However, we do include them as they help with the positioning of the main bars. It is seen that the required anchorage of 500 millimeters is easily achieved. Under Category 3 checks, we are often quizzed on the pull-out force in the radial pins. As the reinforcing cage moves with the deformation of the barrel, there is little or no pull-out force in the pins. We have experimented with only circumferential reinforcement, and that always stays in the slot with no pull-out. Three tests were carried out at the Transport Research Laboratory on a 5-metre span, 2-metre wide, 3-ring brick arches built with Swanage handmade bricks and lime mortar of 1.3 newtons per millimetre strength, and sand between the rings of the barrels to simulate ring separation. Each barrel was loaded to failure at the quarter point in increments of 10 kilonewtons. It's important to recognise the limitations of these tests. The mortar was fresh, so the barrels would exhibit more strength and be more flexible than, say, a 100-year-old barrel. The fill was Type 2 road base ballast and completely uniform, unlike the variable material found in most real-life bridges. It hadn't had traffic running over it for 100 years, and so wasn't consolidated to the extent of a real-life masonry bridge. There was no blacktop to act as bellows for water pressure, and no percolation of water to wash out fines in the fill and the mortar. There was also no deformation and no settlement of the barrel. However, it wouldn't be possible to find identical barrels on which to carry out tests to failure, and the 5-metre span is greater than some of the bridges we've strengthened, so scaling effects are minimised. The unreinforced barrel was tested to failure at 200 kilonewtons, but not to collapse. Our ASARC software, with all the partial safety factors removed, gave the failure load for the load at the quarter point as 190. So it's pretty close. With the partial factors reset, this gave a highway loading capacity of 7.5 tons. The failed unreinforced barrel was then jacked back into place, and the bottom ring only was reinforced. This increased the capacity by 38% to 276 kilonewtons. As we have seen, reinforcing the bottom ring only can, in some circumstances, reduce the capacity of the barrel. This test was carried out only to investigate the effect of the radial pins. The MARFLEX software hadn't been written at the time of this test. The later final test incorporated the full MARFLEX system. This test was witnessed by an audience of about 70 invited engineers representing the major bridge owners of the country. The MARFLEX software was available, and the amount of reinforcement installed was designed to give the barrel a highway loading capacity to 40 tons. This was equivalent to a failure load of 349 kilonewtons, which we advertised before the test. The test jack ran out of extension near the end of the test, so the load was released while a longer jack was installed. This probably weakened the barrel to some extent. In the event, the failure load came at 345 kilonewtons, which compared very favourably with the 349 predicted by the software. The MARFLEX software was proved to be accurate, not only from these tests, but also from independent Category 3 checks using nonlinear finite element analysis. With actual bridges, it is important to carry out sensitivity studies on the various parameters mentioned to relate the software to the actual bridge. The deflection profiles show that the MARFLEX system reduces the deflection, but because only small diameter bars are used, the barrel retains flexibility. These tests were part of a TRL program of comparative tests on the various strengthening methods: sprayed concrete soffit liner, concrete saddles, Pali-Radici pile strengthening, Helifix system, and the MARFLEX system. As we have seen, the sprayed concrete soffit liner restricts the aperture, and concrete saddles are expensive, disruptive, and just not environmentally friendly. The Pali-Radici pile test resulted in the bottom ring breaking away, and the Helifix test wasn't a success. Helifix now use the MARFLEX system. Whilst we were installing the system in this bridge in Gloucestershire, the County Bridge engineer, Liz Kirkham, invited the BBC to visit the site and feature the MAR system on the One Show. Dick Strawbridge demonstrated the system for the programme with Liz in the background. This is us posing. I'm the good-looking one on Dick Strawbridge's left. So, the MAR system, it won the Design Council's Millennium Award for Innovation. The system was displayed on the Spiral of Innovation at the Millennium Dome as an example of the very best in British ingenuity. That's why we put the Millennium Products label on our publicity. It's designed using well-proven in-house software. It uses materials that don't degrade, so it's long-lasting. So in summary, the system doesn't add weight to the structure, doesn't reduce the elevational area, doesn't significantly alter the appearance of the structure, and doesn't require a road closure or inconvenience the travelling public. The system also is durable. It utilises the inherent strength of a barrel, so requires minimum additional material. It preserves the inherent flexibility of masonry arches. It improves the structural behaviour and elastic response. It cures or prevents ring separation, which is the principal mode of failure under cyclic loading. It's cheaper than other practical alternatives. Operations can be planned sequentially to minimise inconvenience to users. Alterations to statutory undertakings are not required. It's easily inspected and repaired. It preserves biodiversity, and it's the most environmentally friendly method of masonry arch rehabilitation. Thank you for your attention. I hope I've given sufficient explanation of how the MAR system works and why it has to be the go-to method of masonry bridge repair and strengthening. Others have tried to copy the concept of the MAR system, calling it, for example, near-surface reinforcement, but without any real success. I must admit I'm concerned about some recent statements by those who appear to be leading the thinking on masonry bridge assessment and design rules. As previously mentioned, SSP carried out numerous load tests on existing bridges using the methods mentioned previously. We found that the rules and the codes are, in most cases, conservative, but this enables the assessment engineer to sleep at night, knowing that he or she is protected by a comfortable safety margin. Current moves to chip away at the comfort margin will make life very difficult for the assessment engineer. I'm concerned that bridge inspection has, in many cases, been reduced to form filling. Every bridge is different, and it's important that the inspector gets a feel for the bridge and how it behaves under load. Being armed with a bunch of forms on an electronic device takes away the focus from understanding the bridge to form filling. We regularly come across inspection reports that, in addition to copious forms, also meticulously log defects without any thought as to what's causing these defects, which is essentially a waste of client money. Photos are good, though. This is the last in the current series, though I'm hoping to add further lectures on the history of masonry bridge construction and rules of thumb and methods that were used to build them. Thank you.